Okay, let's start. It's a great pleasure to have Professor Bernhard Keller to tell us about from Coxeter-Conway friezes to cluster algebras. Let's welcome.
Thank you very much, and many thanks to the organizers of this amazing conference for the kind invitation and this opportunity to speak. In this talk, I have two aims. I would like to make a bit of propaganda for cluster algebras on the one hand, starting from elementary examples. No, it doesn't seem to work. Okay. Namely, first of all, I would like to introduce Coxeter-Conway friezes and then observe their remarkable properties, and then in a second time show how these remarkable properties come actually from properties of cluster variables, which are vast generalizations of the entries of Coxeter-Conway friezes. And then in Coxeter-Conway friezes, we will also observe a remarkable periodicity phenomenon. And in the second, in the last part, I'd like to present a general periodicity theorem, which generalizes the periodicity observed in Coxeter-Conway friezes. And now the plan is as follows. I'd like to start with a general overview of the location of cluster algebras within mathematics in the mathematical landscape. Then I would like to present Coxeter-Conway friezes, then their generalization in cluster variables, and finally the periodicity theorem. And I'm sorry, I think I'm using the wrong file here, so let me just quickly change to the other file. Sorry for this. And for this error, so let me see here. Oh. Okay, no. Yes, sorry. I think maybe there's an error here. Sorry, I will update it. Yep, sorry. I have to. This is the wrong version. Yes, by the way. Yes, so in the meantime, if you want to download the slides, you can use this QR code or the link, bit.ly link. While it's compiling. So the slides which you find at the link are the handout slide, and that should be the correct version. Okay, then let me get back to. Okay. Let me get back to. Yep, this is 1105, so this should be correct. Okay, is it? It is 40 megabytes on your telephone? Okay, let me not try to, to decrease the size now. Um, yes, yes, so here again we have the plan, and I'd like to start with the location of cluster algebras in the general landscape of mathematics. Well, cluster algebras are certain commutative algebras endowed with a rich combinatorial structure. They were invented by Sergei Fomin and Fomin-Zelevinsky at the beginning of the 2000s. The first paper appeared in 2002. And I will give the definition in a second. And when you see the definition, you will agree that it's an invention rather than a discovery. And the motivation for this invention came from Lie theory, and more precisely from the theory of canonical basis in quantum groups and the related theory of total positivity in algebraic groups. Both theories are essentially due to George Lustig from the beginning of the 90s. Canonical bases are certain remarkable vector space bases in quantum enveloping algebras. They have wonderful properties, but they are extremely hard to make explicit. And one of Fomin-Zelevinsky's hopes was to develop an explicit and combinatorial approach to the construction of such bases, or at least to the construction of a large part of such bases. Now, soon after their invention, it turned out that the cluster algebras are also relevant in a large array of other subjects in mathematics. Maybe the first one was in Poisson geometry. When you have a Poisson variety with a compatible cluster structure, then you have what are called log canonical coordinates. So these have the property that the Poisson bracket just becomes a quadratic expression with constant coefficients. This was in particular investigated by Gechtmann, Shapiro, and Weinstein. Then related to this, we have the use of the cluster formalism in higher Teichmüller theory by Fock and Goncharov. Fock and Goncharov reinterpreted Fomin-Zelevinsky's ideas and in a geometric framework and applied it to construction of higher Teichmüller spaces. And in particular, they came up with a series of duality conjectures which were highly influential and are now understood and related to mirror symmetry. Then another important connection is to certain discrete dynamical systems, the so-called Y systems and T systems. So for example, using cluster combinatorics, Fomin and Zelevinsky were able to prove a periodicity conjecture by Alexei Zamolodchikov from the early 90s on the periodicity of Y systems associated with Dynkin diagrams, and I will come back to this later. I will come back to a generalization of this periodicity theorem. Then there are several links to algebraic geometry. The first one was discovered by Kontsevich-Soibelman in 2008. They interpreted cluster transformations in the framework of Donaldson-Thomas invariance. This was then expanded by Nagao. Another more recent connection discovered by Gross, Hacking, and Kiel is to mirror symmetry in the Strominger-Yau-Zaslav approach. And this connection was then applied by Gross, Hacking, Kiel, and Kontsevich to prove several important theorems about cluster algebras, the positivity theorem, and they also constructed what they called canonical bases, but which ultimately turned out to be very different from Lustig's canonical basis. Okay, from the beginning, the link to combinatorics is very important. Cluster algebras are essentially combinatorial in nature, and another link to combinatorics is via combinatorial polyhedra, like the star-surf associahedra. So from the cluster formalism, Fomin-Zelevinsky and Chapoton constructed generalizations of associahedra for every finite root system. Now, all these links and the link to representation theory, which I will come back to in a second. All these links were discovered between 2000 and 2012, and people expected that that would be it. People didn't really expect a new link, but surprisingly, about 4 years ago, a new link was discovered to symplectic topology. It turned out that the cluster formalism is highly relevant to the study of Legendrian knots and their Lagrangian fillings. There's important work by Roger Casals and Honghao Gao, who prove the existence of infinitely many Lagrangian fillings for certain Lagrangian torus knots. And so we have an application from cluster algebras to symplectic topology. And conversely, even more recently, ideas from symplectic topology were used by Casals and collaborators to prove conjectures about cluster algebras, the existence of cluster structures on the so-called braid varieties, which gives a proof of a large generalization of a conjecture by Leclerc from 2016. So now let me come to the link to representation theory. So here the link is in the spirit of categorification. We try to interpret the combinatorics of cluster algebras as the shadows of phenomena which already occur at the level of categories of representations. And then sometimes, thanks to the rich structure of these categories, we can prove theorems, purely combinatorial theorems, but which seem to be outside of the purely combinatorial methods. And, well, to be more precise, there are two types of categories which are used here. On the one hand, monoidal categories. And here the idea is very simple. We try to establish an isomorphism between our cluster algebra and the Grothendieck ring of a suitable monoidal category in such a way that the cluster combinatorics correspond to the combinatorics of the simple objects in our monoidal category, more precisely the prime simple object, the real simple objects, but anyway. And well, such monoidal categorifications are very hard to construct. Yes, they were invented in 2010 by Leclerc and Hernandez, and they came up with the first small examples. Yes, so they're very hard to construct, but when they exist, they give immediately powerful results, and in particular, they allowed to confirm Fomin-Zelevinsky's main hope on a link between cluster algebras and Lustig's canonical basis. This was due on the one hand to Fan Xian in 2017, a little bit later and largely independently by Kang, Kashiwara, Kim, and Oh. And well, on the other hand, we have categorification via triangulated categories. Here the link to the cluster algebra is much more involved. On the other hand, these categorifications are easier to construct, and when we have them, it is more difficult to derive consequences. But nevertheless, there's at least one very nice application, namely a generalization of Fomin-Zelevinsky's periodicity theorem. So using this link, we get a periodicity theorem for pairs of Dynkin diagrams, and I will come back to this later. And so you see that, well, cluster algebras allow us to build bridges between different subjects, yes, which are usually very fruitful. Here I have given you two examples, both linked to representation theory because that's the subject I come from, but there are many others. Okay, so now let me come to the first completely elementary manifestation of cluster phenomena. In friezes, in the Coxeter-Conway friezes, well, first of all, in architecture, a frieze is a horizontal repeating pattern, like here under the roof of a temple, or here below a bridge. This is an example from Nanjing. I took this picture a few years ago. Now, in mathematics, a frieze, a Coxeter-Conway frieze, is constructed recursively, starting from initial data in the form of such a snake of ones which border an infinite strip, which is infinite to the right. And starting from these initial data, we fill up the strip with numbers using the following recurrence rule. When we see such an angle of 3 numbers, we complete it by putting 1 plus y times z divided by x in this corner. So if you bend your head a little, you see that this means that the determinant of this square matrix is equal to 1. Okay, let's look at an example. So here we see such an angle. So 1 times 1 is 1, plus 1 is 2, divided by 1 is 2. Here again, we get 2, of course. Then 2 times 2 is 4, plus 1 is 5, divided by 1 is 5. And now here, 5 times 1 is 5, plus 1 is 6. And remarkably, 6 is divisible by 2 with quotient 3. And so, well, we have this rational recurrence rule, but we find an integer. And of course here as well. And then here, 3 times 3 is 9, plus 1 is 10, divided by 5. Again, 10 is divisible by 2, surprisingly, and so by 5, and we get a quotient 2. Yes, and then we can continue. Here we get 1, 1, then here 1 times 1 plus 1 divided by 2 gives us 1. And so you see that the initial pattern reappears here. Yes, and well, and then of course the computation repeats. And we fill up our strip in this periodic way. Yes, this is a first example of periodicity. And well, this works whenever for arbitrary initial data. Yes, here we have a snake of ones of a different shape. And again, we can perform this completely elementary computation. Yes, you can explain it to the primary school student. And okay, here we find 1 again, and then 1 times 2 plus 1 is 3, divided by 1 is 1 again, and 1 times 1 plus 1 is 2, divided by 2 is 1 again. And so we see the initial pattern reappears, and now we see that the periodicity is actually with respect to a glide reflection, which we didn't see in the first example because the initial pattern was symmetric. And so we have periodicity with respect to this glide reflection. And then, so the remarkable phenomena are that we find integers and that we get a periodic pattern. Okay, and now we can, instead of doing this with numbers, we can generalize to indeterminates. Well, we will keep the ones at the top and at the bottom, but we use indeterminates for the left border. We use exactly the same recurrence rule. Yes, so 1 times x2 plus 1 divided by x1. This times 1 plus 1 divided by x2 gives us this. And then here, 1 times this expression plus 1, well, that gives us a certain Laurent polynomial. And remarkably, this Laurent polynomial is divisible by 1 plus x2, so that the quotient is again a Laurent polynomial. So the denominator is a monomial instead of a complicated polynomial involving 1 plus x2. Yes, and then, well, we continue the computation. If you do it, you see that here you find x1, and here you find again x2. So again, we have periodicity for this glide reflection. And okay, so the computation continues. So the first remarkable fact is that we find Laurent polynomials. All denominators are monomials. And this, of course, implies the numerical divisibility, which we saw. If we specialize the initial x1, x2 to 1, then all the denominators will become 1, and the quotients will remain integers. So that's the first remarkable phenomenon. And then the second remarkable phenomenon is this periodicity, which we have even at the generic level. Okay. Yes? Here they're all 0 and 1. Yes, that's, yes. This is not something which will generalize. The thing which will generalize is that they are positive integers. Yes. Yeah, this is the positivity theorem which I mentioned, and yeah, which is very hard to prove. Okay, more questions or observations? Okay, so these are, in fact, as we will see, these are examples of cluster variables. So this recursion scheme is a very special case of a very general recursion scheme, which defines the microphone up. Okay, thank you. Is it better now? Yeah, thank you. Yes, yeah, okay, so these are, I claim that these are special cases of cluster variables. Cluster variables are defined recursively by a much more general recursion scheme. Okay, and well, here you have pictures of the inventors of the whole theory. Andrei Zelevinsky sadly died in 2013, just a few months before the conference celebrating his 60th birthday, which then was turned into a memorial conference. But Sergei Fomin is alive and well and highly active. He will take part in a big conference in Shanghai in 2 weeks' time. And well, the basic combinatorial ingredient which we need to construct a cluster algebra is that of a quiver. Well, if English is not your mother tongue, you may not know what a quiver actually is in everyday life. A quiver is a container for arrows. Yes, here you can see an example from Iran, a picture I took in 2010 when it was still possible to travel to Iran. Pardon? Right, I was going to ask who recognizes this mathematician. Yes, and Artan immediately recognizes Hirako Nakajima, the president of the International Mathematical Union, and more importantly, the inventor of Nakajima quiver varieties. And for his 50th birthday, his students offered him this beautiful Japanese-style quiver with especially long arrows. Okay, so this is a quiver in everyday life. Now, a quiver in mathematics is an oriented graph. Yes, so it's given by a set of vertices, then a set of arrows, and for each arrow we give ourselves its source and its target. So if you like, you can think of a quiver as a category without composition. So here we have an example. A quiver can have several connected components. Of course, the set of vertices here is just a set of integers from 1 to 7, and we have the arrows. And let me introduce a bit of terminology. A loop in this subject is an arrow going from a vertex to itself. A two-cycle is a pair of distinct arrows going back and forth between two not necessarily distinct vertices. And then we have the notion of a source. 7 is a source, a vertex with only outgoing arrows, and dually 6 is a sink, vertex with only incoming arrows. And now to define the cluster variables, I need to fix the initial datum in the form of a finite quiver without loops and without two cycles. And I will, for simplicity, I will always assume that the set of vertices is the set of integers from 1 to n. Okay, and now we need to introduce an elementary operation on this type of quiver mutation. We choose a vertex of our quiver and we define the mutated quiver, mutated at the vertex number j. It's defined in 3 simple steps. In the first step, we look at such subquivers, paths of length 2, passing through the mutating vertex. And for each such path, we add a kind of formal composition, a new arrow, which we can view as formal composition. Then in the second step, we reverse all the arrows passing through the mutating vertex. And well, by adding these new arrows in the first step, we may have created two cycles. We don't want them, so we just remove them in the last step. So for example, if we have 3 arrows going back and forth between two vertices, we simply choose 2 among them and throw them away. And this, of course, is not completely canonical, but it's canonical up to isomorphism fixing the frozen vertices, and that's enough for our purposes. Okay, so let's look at a simple example. Yes? No frozen vertices in this talk. Yeah. Okay. More questions? Frozen vertices. Yeah, frozen vertices are vertices at which you never mutate. Yes. So yes, so there are more advanced variants of the construction where we have frozen vertices and valued arrows, but I will keep things simple. So let's take this 3 cycle and let's mutate it at the vertex number 1. Let's go through the 3 steps one by one. Yes, so in the first step, we have to look at the paths of length 2 through the mutating vertex. And we have to add one formal composition. Then in the second step, we have to reverse these 2 arrows incident with the mutating vertex, like this. And in the third step, we eliminate the unique 2 cycle, and so that's the result. Okay. And now, well, it's important to do bigger examples. And well, for this, you can download an applet at this link. Pardon? It should be less than half. It should be about 500 kilobytes. This applet. Okay, so I have a local version here. Okay. Well, this example is a bit too big to start with. Let's start with the one we have just done by hand. Okay, there's 3 cycles. So, well, in the applet, we mutate by clicking on the vertices. So if I click at this vertex number 1, then these 2 arrows, then this arrow should disappear, and these 2 arrows should be reversed. Let's try. Click, and indeed, this is what happens. If we do it again, click, well, we get back to the original quiver, and you can show as an exercise that indeed mutation at a fixed vertex is an involution for an arbitrary quiver. Then, well, what happens if we mutate at a source, for example, this vertex, yes? Well, we have no incoming arrows, so nothing happens in the first step. Then in the second step, we reverse this unique outgoing arrow, and in the third step, nothing happens. There are no 2 cycles. So the overall effect is just to reverse this unique outgoing arrow. Click. And more generally, yes, when we have a source, mutating at the source reverses all the outgoing arrows, like this. And mutating at a sink reverses all the incoming arrows. Okay, so well, I think we have understood this first simple example. Let's look at the next bigger one. Okay, this is much more complicated, just glued together from 4 3 cycles. But I claim that I can transform it into a tree by just 4 mutations. Okay, and so before doing that, let me deform the picture slightly. Yes, this has no incidence on the quiver. The quiver is an abstract graph, but the pictures will look nicer. So what is going to happen if I mutate at this vertex? Well, quiver mutation is essentially a local operation, and the thing that's going to happen locally is the thing that happened in the first example. So these 3 cycles have to be transformed into chains. These 3 arrows have to disappear. And here we have this chain at the bottom, so it has to be transformed into a 3 cycle. A new arrow should appear here at the bottom. Let's try. Click. Yes, indeed. The 3 arrows have disappeared. We can easily, well, we want to transform it into a tree. We can easily get rid of this 3 cycle by mutating here. Click. And then we have this 4 cycle. Well, we first mutate here. Click, and then here. And now, okay, you can see we have indeed found a quiver whose underlying graph is just a tree. Yes, there's a graph layout algorithm built into the applet. It's more useful in bigger examples, of course. So you recognize a nice tree with underlying graph, the Dynkin diagram of type D6. Okay. And now, well, these first examples look very nice and simple. But in fact, quiver mutation is an extremely complicated operation. So let me try to convince you of this by looking at a bigger example. Yes, so this is quite big. Well, we can try and play with it, but it's not really clear what to do with it. So let's do something random. Let's do, let's say, 15 mutations at randomly chosen vertices. Okay, we get some changes. Let's do it again. Okay, some more changes. And again. And now you can see we have numbers which have appeared. Yes, here we have this 2 on this arrow. This 2 means that it's actually a double arrow. It's 2 arrows going from this vertex to this vertex. And here we have another one. So let's do 15 more random mutations. Right? Yeah, so now I have many multiple arrows. Yes, I have arrow here. I have an arrow with multiplicity 4. Yes, so the multiplicities grow. Let's do 15 more random mutations. And you see that they grow and grow and grow. And you get this explosion. And this is the typical phenomenon which occurs. So if you have, this is an example of a wild quiver. Almost all quivers are wild. And if you perform random mutations on a wild quiver, you get this type of explosion. So it is a very complicated operation when you iterate it. Okay. Well, here you can see 3 quivers which are mutation equivalent. You can get from one to the other by a finite sequence of mutations. Yes, they look very different, but they are equivalent. And yes, I mean, my initial aim in writing this applet was to get an intuition for when 2 quivers are mutation equivalent, and I have completely failed in that respect, but the applet has nevertheless turned out to be useful. Okay, well, we wanted to define cluster variables. So, and in order to do that, we need to enrich the purely combinatorial datum of the quiver. We need to consider so-called seeds. What is a seed? It's a pair consisting of a quiver with n vertices, and for each vertex, we give ourselves rational expressions in n indeterminates, x1 up to xn. Okay, and these rational expressions should form a free generating set for this field. So in other words, they should define an automorphism of this field. Yeah, so if you like, you can consider this as the datum of a quiver and an automorphism of this field. Yes, so for example, here we have a quiver, and here for the ui's we just take the xi's themselves. Yes, they certainly form a free generating set of this field, and I will abbreviate such a seed by writing the rational expressions in place of the vertices. Okay, and now we can extend the quiver mutation to mutation of seeds. We choose a vertex of our quiver, and we define a new seed, the mutated seed. Well, we have the quiver component. That's just the mutation of the given quiver at the chosen vertex. And now the non-trivial part is the mutation of these expressions ui. And well, we keep all the expressions except the one at the mutating vertex. So we only modify the expression at the mutating vertex j, and we modify it according to the so-called exchange relation. which tells us that the product of the old with the new expression is a sum of two monomials. Namely, we take the first monomial is the product over all incoming arrows at the mutating vertex. We take for each of these arrows, we take the expression at the source of the arrow. And then the second monomial is the product over the outgoing arrows from the mutating vertex. And for each of these arrows, we take the expression at the target of the vertex. So this is the fundamental relation. Yes, so when you're in a situation where you have a product of two things, which is a sum of two monomials, then it's likely that there are some cluster variables and a cluster algebra in the background. Okay, so let's look at an example here as well. So we take this as our initial seed. And what happens if we mutate at the vertex number 1? Well, first of all, at the level of the quiver, 1 is the source of the quiver. We just have to reverse this unique outgoing arrow. And then we have to form the new expression. So we have to look at the two monomials. First monomial over the incoming arrows. There are none. So it's the product over the empty set. The product over the empty set is 1. And then product over the outgoing arrows, there's only this one. Its target is x2. So we get 1 plus x2 divided by x1. And we keep the other expressions. Okay. Well, what happens if we mutate at vertex number 2? Well, at the level of the quiver, this chain is transformed into a 3-cycle. Then we keep the expressions associated with the non-mutating vertices. And then here, well, we take the product over the incoming arrows. That gives us x1 plus the product over the outgoing arrows. That gives us x3. And we divide by x2. Okay, and similarly for mutation at the third vertex. And now, of course, we can iterate this procedure. Well, for example, if we take this and mutate again at the vertex number 1, we will get back to the original seed. Mutation at the fixed vertex is an involution for seed mutation as well. And then, yes? Only one guide changes at each mutation, right. Right. Okay. So if we mutate at 2 or 3, we get potentially new seeds. And, well, in this way, we get an infinite tree whose to each vertex of this tree is associated a seed, and in particular, a triple of rational expressions. And by definition, these rational expressions are the cluster variables associated to the quiver we started with. So here we have started with this chain of length 2, and the cluster variables are all the rational expressions which appear in this process. Okay, so let me give you the general definition. Yes? Yes? Yes, well, to make things less confusing, to make things... Pardon? I mean, well, the x's are the generators of this field. They are fixed once and for all. And now I construct new expressions. So I always start from the x's, and then by successive mutation, I construct lots and lots of expressions. And these expressions are called U. No. So yeah, thank you for the question. Okay, so we start from a given quiver. We define the initial seed to be this quiver with the xi's associated to the vertices. And then we do the process as in the example. We mutate, and by mutating, we generate lots and lots of rational expressions in the xi's, and these are the cluster variables associated with our quiver. And the cluster algebra is the subalgebra of the function field generated by all the cluster variables. Okay, but, well, I will not speak about the cluster algebra. I only speak about the cluster variables. And now the first fundamental theorem is that all the cluster variables are Laurent polynomials, yes, which is not clear at all from the rational recurrence rule which we have used to define them. Okay, and then secondly, well, the coefficients are non-negative. Yes, this was conjectured, of course, by Fomin and Zelevinsky from the very beginning, but then it took 11 years to prove it in the case of quivers, and well, another 5 years to prove it for the more general case of valued quivers. Yes, valued quivers are to quivers what non-simply laced Cartan Dynkin diagrams are to simply laced Dynkin diagrams. Yes. Yes, there is a topical version, and this is very important, but I will not speak about it. Yes, so this was proved, the positivity was proved for Lee and Schiffler in 2013, and then using combinatorial methods, so they wrote down explicit formulas for cluster algebras associated to quivers with 3 vertices, and from that they deduced the general case. Then Gross-Hecking, Kiel, and Kontsevich proved it in the general case using methods from mirror symmetry, yes, theta functions and broken lines. Okay, well, and then there is the notion of exchange graph. Yes, I mentioned combinatorial polyhedra at the beginning. This is, here you see a picture of the third Starshev associahedron, yes, invented by Starshev in 1962. He invented A infinity spaces at the same time as A infinity algebras. So this is the corresponding Starshev associahedron, and this surprisingly appears in this theory. Each vertex of this associahedron is associated with a seed up to simultaneous renumbering of vertices and variables, and each edge corresponds to a mutation. Yes. And so if you look at these exchange graphs in type A, you get the family of Starshev associahedra, and then you can look at other types and get the generalization of Chapoton Fomin-Zelevinsky. Okay, but now I claim that Coxeter-Conway friezes are formed by cluster variables, which will give a proof of the fact that we do get Laurent polynomials here. And how does it work? Well, you remember the recurrence rule. So where is our quiver? Well, our quiver is here on the left. Yes, this is our quiver. And this is also the initial seed of a cluster algebra of type A3. Now, if we take this quiver and mutate at the vertex number 1, yes, so this is our initial seed for this quiver. If we mutate at the variable number 1, then the mutation rule for this variable is exactly given by this recurrence rule. And so mutation passes from this initial seed to this new seed, x1 prime. The x1 prime is exactly, on the one hand, given by this rule, and on the other hand, given by the mutation rule. And now if we mutate at 3, yes, then we find a new variable here, etc. Yes, so mutation of seeds is exactly mutation of seeds at this very special sequence of mutations is exactly given by this recurrence rule. Yeah, so and then we find we also find periodicity. Again, yeah, this is not yet in Fomin-Zelevinsky's theorem. Yes, so we do find this periodicity up to applied reflection, and it repeats. Okay, so we have seen periodicity, and now we had Fomin-Zelevinsky's theorem on the Laurent polynomials, and now I'd like to give the theorem on periodicity. So for this, I need to recall the Dynkin diagrams. Yes, so we have two infinite families of simply laced Dynkin diagrams: the AN family and the DN family, and with each diagram, there's associated its Coxeter number. Here's the order of the Coxeter element in the while group. Here you can just take this as the definition. And then we have E6, 3 exceptional diagrams, E6, E7, and E8 with Coxeter numbers 12, 18, and 30. Okay. And so periodicity will occur when we start with a quiver whose underlying graph is a Dynkin diagram. Yes? Yes?
Mutations are the variables, right? It's not the variables that are vertices. Because then what does it mean for division by x?
Division, well, I'm in my function field in n indeterminates. I have my initial seed where the ui's are the xi's associated to the vertices, and then I perform mutation according to the rule. And mutation is just some rational rule which I perform in my ambient function field. Yes, let's go back.
What does it mean, mutating the graph at x?
Well, so this on the left, this is a picture of the seed, of the initial seed associated with this A3 type quiver. So this is the initial seed. The quiver is this one, and with each vertex with each vertex I, we have associated the variable xi. And then the mutation rule says that if we mutate this initial seed, we have to mutate the quiver. So this arrow in this direction is changed into an arrow in this direction. So here it was incoming to vertex number 2, and here it is outgoing from. And now this expression, this is a new expression. Yes. So in the mutation rule for seeds, it's the expression given by the exchange relation. And as you can see, the exchange relation in this case, yes, if you remember, this is 1 plus x2 divided by x1. So this exchange relation for the cluster variables specializes to this recurrence relation in the Coxeter-Conway frieze. Yeah, absolutely. I use a very special sequence of mutations to construct the frieze. Pardon? Only I always mutate at the source. I mutate, yes. So here, this was one was a source. Yeah. Here I mutate at the source 1, and now I mutate at the source 3. Now I mutate at the source 2. Yes. So the mutations are of the simplest possible type. They are always source mutations. Okay. Yes. So and we will see now periodicity whenever we start from a quiver of Dynkin type, and we perform mutations at sources. Yes, so let's take a Dynkin quiver, a quiver whose underlying graph is a simply list Dynkin diagram, for example, this A3 diagram, and then we choose a source sequence. Yeah, so a source sequence is a sequence which is increasing for the natural order induced by the arrows. Yes. So yes, so this is our sequence here. For example, 1, 3, 2 is an increasing sequence for the natural order, an increasing enumeration of the vertices, and we define a composed mutation by composing the mutations at this increasing sequence of vertices. So this could be, here it would be mu1, mu3, mu2. And then the theorem, Fomin-Zelevinsky's theorem, says that if we take this composed mutation sequence and apply it h plus 2 times to the initial seed, we get back to the initial seed. So, for example, so this is the theorem. And now let's do this for the initial quiver of type A3. Yes, so we have to apply this mutation sequence 1, 3, 2, and we have to apply it h plus 2 times. Well, what happens if we apply it once? Yes, so we mutate at 1, then at 3, and then at 2. And so you see that applying this mutation sequence just corresponds to performing one translation to the right in the Coxeter-Conway frieze. Okay, and so the theorem says that if we do this h plus 2 times, we have to find the initial seed. Well, so this is A3. The Coxeter number of A3 is 4, yes. So if we do this 6 times, if we perform 6 times this sequence, we should get back to the initial seed. So let's see, 1, 2, 3, 4, 5, sorry, 1, 2, 3, 4, 5, 6. And yeah, as you can perform the computation and you see that you get back to the initial seed. So periodicity of this Coxeter-Conway frieze is a consequence of Fomin-Zelevinsky's theorem. And notice that this is the square of the glide reflection, which we observed at the beginning. So yeah, it can be refined. But anyway, so yeah, so we get this periodicity. And now, well, this is a very nice theorem, but it's also a bit strange, yes? It's strange because of this exponent h plus 2, yeah? H is the order of the Coxeter element, so you would expect periodicity with period h rather than h plus 2. What is the meaning of 2 in this exponent? And well, 2 is the Coxeter number of the Dynkin diagram A1, yes? Coxeter number of an is n plus 1, and in particular the Coxeter number of a1 is 2. And so actually in this formula we have 2 Coxeter numbers, and so it is natural to try and generalize the theorem using a pair of Dynkin diagrams rather than a single diagram. Let's take 2 diagrams, and now, well, we have to produce the analog of the special mutation sequence for a certain quiver. Okay, so, and the quiver which we take is the so-called square product. Okay, now this may look a bit arbitrary. Of course, the whole thing is motivated by conjectures from the 90s, conjecture by Alexei Zamolodchikov, and then generalized by his readers to pairs of Dynkin diagrams. And so if you take these periodicity conjectures for the corresponding Y and T systems and translate them then into the quiver language, then you end up with this quiver. So what is the mutation sequence we take? We take, on the one hand, first mutation at all the wide or even vertices, and then mutation at all the odd vertices. And mutations at any 2 vertices in the same group commute because there are no arrows between any 2 white or 2 black vertices. So we take this sequence and we compose it, and if we perform it h plus h prime times and apply it to the initial seed, then we get back to the initial seed. Yes. So this is the confirmation of the generalization of Zamolodchikov's periodicity conjecture from the early 90s. So Fomin and Zelevinsky had the case of a single Dynkin diagram, and here we have it for pairs of Dynkin diagrams. Yes, yes. Yes, one can generalize, but for the purposes of the talk, it's best to choose this particular orientation. Okay. Well, I mean, before the theorem was proved, people tried, for example, to check it using a computer. Yes. Well, if you try to check this on a computer, well, already this diagram is too big for this small computer to check. And if you take slightly bigger diagrams, then in the computations you will get expressions where the number of terms exceeds the number of atoms in the universe. Well, that's so the computer will fail. Now, fortunately, there is a variant of this theorem, which in some sense is tropical, which is purely in terms of quiver combinatorics. So we take our square product and we enlarge it. We add a few more vertices and a few more arrows so that the initial quiver is a full subquiver. And then we have the same statement. If we apply mu plus mu minus h plus h prime times to this larger quiver, it will transform the larger quiver into itself. So, and this is something we can easily check on a computer. So let's check it, for example, in types A4 and A3 with Coxeter numbers 5 and 4, whose sum is 9. Okay, let's have a look. Q tilde is arbitrary. It just has to contain Q as a full subquiver. So whenever we have two vertices in the subquiver, the arrows in the subquiver are exactly the same as the arrows in the big quiver. Okay. Okay, so here we have A4 square product A3. So that's the quiver Q, and we have added a few more vertices and a few more arrows. The blue vertices have been added. And now, well, we have the even vertices and the odd vertices. Yes, these are the even ones and the, yes? Yes, that's the statement. Yes, yes, yes. That's fine. That's fine, and that yeah, no problem with that. Yes. So here we have the now blinking the odd vertices. So if we first mutate, say, at the yellow vertices and then at all the red vertices, and if we do the composed mutation 9 times, then that composition should transform this quiver into itself. Okay, so let's try. So I can perform this composed mutation by clicking on this plus button. So let's try. So after 9 times, we should get back 1, 2, 3, 4, 5, 6, 7, 8, 9, and indeed it works. Now type A is very special, yes, as you know, type A is really special. So we should try an exceptional example as well. Let's try E6 and E7. Yes, okay. E6 and E7, yes, with Coxeter numbers 12 and 18, whose sum is 30. Okay. Okay, so again in red we have the square product of E6 by E7. Well, it's a bit more complicated, but if you look at the bottom row, you recognize E6. And if you look at the first column, you recognize E7. Okay, again, we have the two types of vertices, even and odd. Okay, and I can perform the composed mutation by clicking on this plus button. And okay, so let's take 30 seconds to check this. But before let's notice that this arrow is outgoing from the blue vertex. Yes, yeah, actually all of them are outgoing, yes, but in particular this one. Yeah, I could choose anything. I have chosen this picture just to make the things not too complicated in the initial quiver Q tilde. Okay, so this is outgoing anyway. And so let's perform 30 times the composed mutation. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is not the initial quiver because this is in the wrong direction. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and indeed we're back to the original quiver after going through some complications. Okay, and yes, so let me say a quick word on the proofs. So Fomin and Zelevinsky's proofs are purely combinatorial, and through their combinatorial genius, they were able to prove the case of a single Dynkin diagram. Now, if we want to prove the general case for the pairs, then we use category theory and homological algebra as indicated in the title of this section. So the key role is played by the so-called cluster categories. And to link with one of the main themes of this conference, these are certain two-Calabi-Yau triangulated categories. And well, I'd like to show you a picture of one such category. Let me see, I hope I can find it here. Yeah, it was, let's see. Yes, here it is. Right. So this is a picture of a cluster category. The cluster category associated with any orientation of the Dynkin diagram E6. Yes, so these edges should all be arrows, all pointing in the same direction. And well, how is this a picture of a category? The cluster category is a triangulated category. In particular, it's additive, and the Krull-Schmidt theorem holds every object is a sum of indecomposables in a unique way. So it's enough to know the indecomposables, and the indecomposables are in bijection with these vertices. There are 42 vertices. They are in bijection with the indecomposables, and the arrows indicate the so-called irreducible morphisms. Yes, the space of irreducible morphisms is analogous to m modulo m squared in a local ring. And in fact, it turns out that you can give a presentation of the category starting from this diagram, yes, starting from the indecomposable objects and the irreducible morphisms. And then you have to impose relations which are given by these meshes. And where is periodicity in this picture? Well, this is a single Dynkin diagram here. Fomin-Zelevinsky's theorem applies. Where is periodicity? Well, periodicity is just the fact that this is a Möbius strip which closes on itself. So applying the composed mutation means that we walk once around the Möbius strip. So that's periodicity in this case. Okay, yeah. The shift functor is periodic. In this case, it's a two-Calabi-Yau category, so shift and tau is the same. And the periodicity autoequivalence in this case is just tau. So the periodicity autoequivalence is just a translation by one unit. So in this case, the shift in the triangulated category happens to coincide with this shift by one unit in the picture. And this also coincides in this example with the periodicity autoequivalence. If you have a pair of Dynkin diagrams, this is no longer the case. They are still related, but different. Yes? More questions? Yes? Mm-hmm. Yes? Well, we have this type of geometry, it is not clear at all how this type of geometry is related to the geometry of the cluster varieties. So the cluster varieties, there are two of them. The A variety would be the spectrum of the cluster algebra. I haven't defined the cluster algebra, but it's the subalgebra of the function field generated by the cluster variables. Yes, I mean, one can say much more, but there is definitely no direct link from this type of picture to the geometry of the cluster varieties. Yes. Yes. Sorry?
For product notation, we have that Coxeter-Conway frieze.
Yeah, so there's here I have started from type E6. If instead I start from type AN, I will also find a Möbius strip. And this Möbius strip should be viewed as the quotient of the Coxeter-Conway frieze by the periodicity automorphism. Yes. Yes. So okay. The Coxeter-Conway frieze is actually a picture of the derived category of the category of quiver representations, and if you quotient by the periodicity auto equivalence, you get the cluster category. Okay. So just to conclude, so here we have a nice example where we use techniques from one subject in order to prove a theorem about a different subject, and the proof is provided by the combinatorial framework of cluster. The bridge is provided by the combinatorial framework of cluster algebras. And well, I have, yes, again, in the spirit of this conference, let me show you a few more pictures of all the people who have participated in the theory in all these different subjects. Yes, so of course we have Fomin and Zelevinsky in the center, then Gechtmann, Shapiro, and Weinstein with the link to Poisson geometry, Fock and Goncharov with higher Teichmüller theory, then here a number of representatives of categorification via triangulated categories, Kontsevich and Seubelmann, who discovered the link to Donaldson-Thomas theory, which was then further developed by Nagao. And here three string theorists, just BPS state counting is closely related to Donaldson-Thomas invariance. Then the inventors of monoidal categorification, Bernard Leclerc and David Hernandez. Bernard Leclerc also appears here. He has worked on both additive and monoidal categorification. Van Zien, who first proved Fomin-Zelevinsky's main hope, and here Kang, Kashiwara, Kim, and O. I'm sorry, there was no space for O, but I can show you the picture separately. And then here, Gross-Hacking Kiel with the link to mirror symmetry in the Strominger-Zaslav approach. Then Fang Li, who together with his student Pagan Cao, proved the last series of conjectures, the denominator conjectures, and then Roger Casals as a representative of the new link to symplectic topology. Because he is so well known that everybody can read the name, even if they don't read Cyrillic. Okay. And there wasn't enough space for the Chinese characters in the names of the Japanese and Chinese mathematicians. Okay. Thank you very much.
Thanks for the very interesting talk. Are there any questions?
If I have the product of these thinking diagrams, I also go in the third direction. So I can go layers and layers of thinking diagrams and cluster. But then at some point, if I loop back into digit A, right?
There is no analogous theorem, for example, for a square product of three thinking diagrams. It just doesn't exist. It is not possible. As far to the best of my knowledge, it is not possible. Yes. This is a bit related to the two-Calabi-Yau property of the cluster category. Yes, the number two.
And then in the vertical direction have an A3 on triangle bar.
You won't get any type of periodicity. No, no. And I mean, of course, when you take very small diagrams, then your quiver will be mutation equivalent to a usual square product of two factors, and then you will get some phenomenon. But in the general case, no. Yes. Another question would be, what do you get if you take affine diagrams, and then, well, you get you can look at the expressions, and you get kind of linear growth in the expressions. whereas in the general case, you get super exponential growth.
Other question?
Can you explain a little bit more about this classification of this object, that the same object corresponds to cluster C?
Yes. Let me see. Right. Yes. So yes. So the link to the cluster category is as follows. So these objects, these indecomposable objects, in fact, they are indecomposable rigid objects. They don't have self-extensions. And the indecomposable rigid objects, these vertices, are in bijection with the cluster variables. There are exactly 42 cluster variables in this case, and they are in bijection, in natural bijection with these, with the vertices or with the indecomposable rigid objects of the cluster category. And what are the objects? Well, in this case, the objects are, the category is obtained as an orbit category from the derived category of the category of quiver representations. And so the objects of the category are the same as the objects of the derived category, so they are just complexes of quiver representations. Yes.
So it was curious, what did Kashiwara and Rogers work with it? What did Kashiwara?
Kashiwara and co-authors, yes, they used monoidal categorification to prove that Fomin-Zelevinsky's main hope is true for a large class of cluster algebras which occur as coordinate algebras on Lie theoretic varieties like double Breuer cells, Grassmannians, partial flag varieties. Yes. Roger, yeah, he was instrumental in the link to symplectic topology. Yes, so together with Honghao Gao, he showed that seeds give rise to Lagrangian fillings. And since in general there are infinitely many seeds, yes, we have seen that there are really infinitely many quivers, mutation equivalent to a given one in general. And since there are infinitely many quivers, there are even more infinitely many seeds. And these seeds, as shown by Casals and Honghao Gao, give rise to Lagrangian fillings, of which there are therefore infinitely many. Yes. And then the other theorem, the application of symplectic topology to cluster algebras, yes, where they use symplectic techniques to prove the existence of cluster structures on braid varieties.
Okay, let's thank Professor Keller again. And it's time for lunch.